Okay, so we are going to solve this problem 346 from Griffiths, third edition. So we are given three matrices. We have to find eigenvalues and eigenvectors, normalized eigenvectors. We are given an initial state. We have to find expectation values. Then we need to evolve this state and find the probability to get some results for our measurements. Okay. I'm going to solve two matrices with you, and then you will see that it's straightforward to do the third one. So the first matrix that we'll talk about is this H. H is from Hamiltonian. Okay, so H bar omega, and we have 1, 0, 0, 0, 2, 0, 0, 0, 2. This is our matrix. Okay, bring this a little bit down. Okay, so this is our matrix. What are the eigenvalues? What are the eigenvectors? Well, the procedure to obtain the eigenvalues is called diagonalization, because what it means is we find the basis in which the matrix becomes diagonal. That's the procedure of diagonalization. That's the procedure that gives us the eigenvalues. You look at this matrix H and you see it's already diagonal. See, you only have non-zero elements along the diagonal, so you don't need to do anything. The matrix is already diagonalized. The diagonal elements are our eigenvalues. Everything is done for us here, okay? So don't waste your time trying to do diagonalization of something that is already diagonal, okay? So what are the eigenvalues? The first one is going to be our first element. This one, but don't forget, we have this h bar omega in front. So this first eigenvalue is h bar omega multiplied by 1. The second eigenvalue is the second one, multiplied by h bar omega. Now the h bar omega belongs to the matrix. So 2h bar omega. And then h3 is the last one, is this one. Yeah, so 2h bar omega. You see that there is something special about this matrix, but which is these two eigenvalues are equal. So we have degeneracy. They are degenerate. Okay. All right. What are now the eigenvectors corresponding to these three eigenvalues that we obtain? It's also very simple. The eigenvector here is just 1, 0, 0. How do I know that? How do we obtain the eigenvectors? We pick the matrix, act on the vector, and we have to recover its eigenvalue and the vector. No? So that's the procedure to get the eigenvector. So you see, here it's very simple. Since the matrix is already diagonal, I just put this vector 1, 0, 0. You can see that if we act with this matrix, h bar omega, 0, 0, 0, 2h bar omega, 0, 0, 0, 2h bar omega. No? If I act with this on that vector 1, 0, 0, I recover. Once I go with this line here, I recover my h bar omega. And nothing else for the other elements because we have zeros everywhere. Yeah, so that's why I wrote that vector. So it's a very simple procedure. For this next eigenvector, again, I can do the same thing. I need to extract that eigenvalue in the second position. So I go 0, 1, 0. And the third one, I want to extract the third, so 0, 0, 1. So these vectors are normalized. If I do h1 with h1, this is 1, so it is normalized, and they are all orthogonal as well. You can see that 1 with 2, 1 with 3 is 0. No? So this is our result. No? So it's very simple to do this problem. Don't waste your time trying to diagonalize. Now, there is something good to keep in mind, which is the following. This is a special case where we have, as we said, this degeneracy. No? These two eigenvalues are equal. So these two eigenvectors that we wrote are correct, but you could use any linear combination of them would also work and give us back this eigenvalue. Okay, but leaving as it is correct. Now let's go to the other matrix. The other matrix is not diagonal. This other matrix is this matrix A, and you see that there will be non-diagonal elements. So this one, yes, you have to diagonalize. You have to do this diagonalizing procedure that will change the basis, put this matrix in a diagonal form. Okay, and how do we do that? Computing that determinant. So let's write the matrix. I'm going to include the lambda now. So we have 0, lambda, 0, lambda, 0, 0, 0, 0, 2 lambda. And what we have to do, I'm going to call the eigenvalues of this matrix A. So we go minus A in the diagonal. And we have to compute the determinant of this. All right? Okay, so we have computing the determinant of this will give us the eigenvalues, 3 eigenvalues. So we have, what we have above is, we can get rid of these zeros, no? Because it's just minus A. And we have to compute the determinant. It helps to some students to rewrite those two first, just put this better here. Okay. So for some students, they like to compute the determinant in this form. They write these two first columns, they just repeat it here. So this is the first column, and this is the second column. And then we go. The product of these elements here. Minus A with minus A gives us A squared multiplied by 2 lambda minus A. Okay, so this is my first element. The second element is this diagonal here, but it's multiplied by 0. So it's 0, we don't need to put it. This last one is also 0, so I don't need to worry about. Then I go now, the off diagonals, and for the off diagonals, we have to put a minus sign. Let me put a different color here. So, okay. So this is the off diagonal. So I have to put a minus sign, and I have lambda multiplied by lambda. So I have lambda squared and 2 lambda minus A. And then I go the other off diagonal elements, no? Off diagonals. So this, but it's multiplied by 0 is 0. This multiplied, there is 0, so it's 0. So the only thing that survives here are these two terms that have to be equal to 0. The determinant has to be equal to 0. Okay, so that's the equation that we have to solve to find the eigenvalues. Let me rewrite like this equation that makes it very easy to see what this eigenvalue should be. This, we have to find the a's that will make this equation 0. So one possible eigenvalue is the eigenvalue 2 lambda. No? This will make this equal to 0. Another possibility is whatever a makes this term 0. So it could be just lambda. It could also be minus lambda. So these are our eigenvalues. So finding the eigenvalues is not too bad. Becomes a little more tedious now to find the eigenvectors. So we will have to go one by one. Okay, so if I want to find the eigenvector corresponding to our eigenvalue A1, what do we have to do? we are going to go matrix, acting on this vector that we are trying to find, which I'm calling alpha 1, will give us that eigenvalue A1, which is 2 lambda, and the vector back. That's what it means to be an eigenvector. All right, so let's try to solve this. Let's try to find this eigenvector. So let me write the matrix A. We have 0, lambda, 0, lambda, 0, 0, 0, 0, 2 lambda. Acting on this vector, I don't know what this vector is, so I'm going to call it x, y, and z. I have to find out what these elements x, y, and z are. Whatever they are, they will appear here again, x, y, and z. Okay, so this will give us a system with 3 equations. With 3 equations, we should be able to find our 3 unknowns, x, y, and z. So what is this system of equation? Well, first line multiplied by the vector will give us the first element there. Okay, so this is many zeros then. Huh? So what really survives is just lambda y, huh, from this product. And this has to be equal to 2 lambda x, the first one. All right, now the second line here multiplied by the vector should give us the second guy. So what is this second line? Lambda with x gives us lambda x, all the others are 0, and this gives 2 lambda y. And finally, the last line with the vector will give us the last guy. So this is 2 lambda z equal to 2 lambda z. So this is our system of equation. All right, so you see lambda appears everywhere. We can get rid of this lambda. And so our system of equation is y equals to 2x. X equals to 2y. And 2z equal to 2z. Right? So what can we do now? Well, this one is very good. 2z equal to 2z makes sense. Now the other two, the only way to make y be equal to 2x when x is 2y, the only way to allow for this to be possible is if x is 0 and if y is 0, okay? Because otherwise it makes no sense, okay? And the other one just tells us that z has to be equal to z. So what should be this vector? Since it has to be normalized, and this is 0 and this is 0, the last element z will be 1. Okay, so for our eigenvalue 2 lambda, the vector is this. Okay, now I'm going to go to the second eigenvalue. So the second eigenvalue is this one. So let's try to find the second eigenvector. Okay, so to find the second eigenvector, we are going to go matrix, acting on this second vector that we are trying to find, will give us that eigenvalue A2. Remember, A2 is lambda, so I'm going to put here lambda. And we will recover back that vector. So we have to solve this. So let's go. Again, same story. 0, lambda, 0, lambda, 0, 0, 0, 0, 2 lambda. Our vector we don't know yet, so I'll call it x, y, and z. Lambda is the eigenvalue, and the vector x, y, and z, we have to find what x, y, and z is. And here we'll have a system of equation. So this line with this vector will give us the first. So lambda y should give us lambda x. Then second line with the vector should give us the second. So we have lambda x is lambda y. And then finally, this multiplied by this, 0 with x is 0, 0 with y is 0, 2 lambda with z give us 2 lambda z equals to lambda x. This guy. All right, so we have our system of equations. Again, lambda is everywhere. We can cancel it. So our system of equations says that y is equal to x. And x is equal to y. Okay, now looks much better. And now the last one, 2z equals to z. Ah, that's strange. The only possibility for this to be true is if z is 0. Okay, and from the other equations, we find the x has to be equal to y. So that means the vector that we are after, this alpha 2, is x, x again, and 0. Okay, x and y are equal, so x. And how are we going to find x? Well, normalization. The vector has to be normalized, so alpha 2 with alpha 2 should give us 1. And so we have x conjugate with x conjugate with 0. That's the bra for alpha 2. X, and 0. Then we have what is the solution of this product? X squared plus x squared plus 0 has to be 1. And so 2x squared has to be 1, means x has to be 1 over square root of 2. So conclusion, for the eigenvalue lambda that we obtain, we got the eigenvector alpha 2, which is 1 over square root of 2, 1, 1, and 0. And then you go, okay, so that's the second eigenvector. Then you go, same procedure to find the third eigenvector. No? And what you're going to be doing now, same procedure, but now using minus lambda, okay? And I let you do this one, but the idea is just the same. You're going to multiply the matrix by this vector that you're trying to find, and the eigenvalue here is minus lambda and alpha 3. And you're going to find after writing the system of equations and so on, that this alpha 3, again, you have to normalize it, and you will find 1, minus 1, and 0. All right, so we have our eigenvalues and eigenvectors. There is one more matrix in this story, which is the matrix B. But if you understood how we found the eigenvalues and eigenvectors for matrix A, you will see that for matrix B is a very similar procedure, okay? Try to do that. If you have any questions, let me know. Okay, now comes next. So this is part A of the problem. It's a long problem because there are 3 matrices. Part B of this problem is, suppose that our initial state is this S0. Is this vector C1, C2, C3. So C1, C2, C3 are complex numbers, and this state is normalized. Now we're always dealing with normalized states, which means whatever these C1, C2, and C3 are, they have to satisfy this. Okay, fine. This is given, and then comes the question. Find the expectation value. Okay, so find the expectation value for the Hamiltonian at time 0, when the system is in this state. How do we find expectation values? Is the sandwich, right? So we just have to solve this. Okay, so this is the expectation value. So how are we going to do that? Well, I'm going to write the bra for that initial state. So the column vector becomes now this line, complex conjugate. No? Then we have the Hamiltonian. So let me write here the matrix. Here we have 0, 2, h bar omega, 0, 0, 0, 2, h bar omega. And the vector C1, C2, and C3. That's what we have to solve. Okay, so it's not hard. The important thing is to remember, how do we get the expectation values? That's how we do it. Now it's the sandwich. We are putting the Hamiltonian between the bra and the cat. Yeah. All right, so how do we do? First, start from the right to the left. So first thing, you solve this one, which is easy. Now it's a matrix. The product of a matrix with a vector will give us back the vector, back the column vector. So h bar omega C1, 2h bar omega C2, and 2h bar omega C3. Okay? And now I'm going to do the product with our bra. Okay, and now the bra with the cat will give us a number. What is the number? First element with first element. Okay, so that's h bar omega C1 square. Then we have 2h bar omega C2 square. And finally 3h bar omega C3 square. So answer of what is the expectation value for the Hamiltonian? Well, we can write it in a simple form like this. All of them have, oops, I put 3 here. Oh, yeah, there's 2, number 2. So all of these terms have h bar omega. Okay, so C1 square plus 2C2 square plus 2C3 square. If you want, no? Put it in a nice form like this. Very good. So that is simple. Let's do one more, which is, what is the expectation value of A for that particular initial state, meaning at time 0. How are we going to do that? The bra, the Hamiltonian, and the cat. Sometimes we put a line here as well. In the book, in the text, we were not putting this line, but many times we put this line here as well. But it doesn't matter, with the line or without, what do we have? Again, the bra is the C1 conjugate, C2 conjugate, C3 conjugate. A is that whole matrix, 0, lambda, 0, lambda, 0, 0, 0, 0 to lambda. And S0, that initial state, C1, C2, C3. All right. So let's multiply these two first. Now start always from the right. So then we have lambda C2, lambda C1, to lambda C3. Okay. And now we'll do the multiplication with the bra. And this will give us just a number. Which number? Well, first element with first element. So lambda C1 conjugate with C2. Next, C2, second element. So lambda C2 conjugate with C1. And finally, 2 lambda C3 absolute value square. So what is the answer? Expectation value of A. All of them have lambda, so I'll put lambda in front. And then we have C1 conjugate with C2 plus C2 conjugate with C1 plus 2 absolute value square of C3, and that's it. All right? And then we can do the same thing for that matrix B. Is that same idea? Very good. Now let's go for the last part of this problem, part C. Given that initial state, what is the evolved state? Yeah. So how do we do that? Well, the general procedure is so the general procedure since chapter 2, what were we doing? We have to find a linear combination. Now we have to put here the components of whatever solutions we had for Schrödinger's equation. So the basis vectors from Schrödinger's equation. And so once we solve this equation, we put here the solutions and attach to it the energies. So this is what we have been doing since chapter 2. This problem here is very simple because the Hamiltonian was already diagonal. And so these eigenvectors are very simple. For the problem that we solved, the eigenvectors were just those 1, 0, 0, 0, 1, 0, and finally 0, 0, 1. So why I'm saying it's so simple? Because what are these components? How do we find them in general? These components are obtained by these eigenvectors that we have from the Hamiltonian, the inner product between these eigenvectors, and our initial state. Yeah, this is the procedure. But here the vectors are so simple that finding these components is very simple. You see, these components, let's try the C1. What is this component C1? It's going to be that vector 1, 0, 0. No? So that's the bra for H1. And the S0. But what is S0? C1, C2, C3. So it's silly to do that because this component is just the C1. Okay? We already have that initial state written in terms of this state. So this is all very simple. I'm going to show another problem where this you have to think a little bit more. But in this case, all that we have to do is the evolved state is just the C1, the C1 for H1 with the eigenvalue E1 T over H bar. Okay, because what is the first element that we get here is the C1. Okay, all right, the next. What is this next element that we are going to do? Now we have to do C2 is the 0, 1, 0, that bra for H2 with that vector C1, C2, C3. So you see, it's silly. It's again just C2. So this is C2 for the H2 with its eigenvalue. And then C3 with that vector with its eigenvalue. All right, so let's write this a little, let's continue a little bit more because we do know what the eigenvalues are. Now we do know what what E1, E2, and E3 are. So let's use that. All right, so then we go C1 that eigenvalue is the first one, so it's minus I h bar omega t divided by h bar omega. No, divided by h bar. So then you see that we can cancel this. Okay, next. C2 e to minus I 2h bar omega, t with h bar, again, this cancels. And finally, C3, same thing here, because these eigenvalues are the general, no, it's again 2h bar omega. And this h bar omega cancels. No? So our state is C1 minus I omega t plus C2 minus 2I omega t and C3. And we can put in that column form. And so we can put this in a, because what is this vector? 1, 0, 0. What is this one? 0, 1, 0. What is this one? 0, 0, 1. So I can put everything in a column form. So it's going to be C1 with the exponential, and then C2 with that exponential, and C3 with that exponential. So this is our vector, evolved state. All right, very good. So we got, but there is one more question. Now comes. So given this vector at time t, which we just obtained, if I measure energy of this state, what values can I get? When you measure a quantity, when you measure an operator, the quantities that you can get are the eigenvalues. Okay? So when we measure an operator, when we measure Hamiltonian, what are the outcomes? What are the values that we can get? Are the eigenvalues. Okay? So if I measure energy, I'm thinking about Hamiltonian. If I measure energy, what are the results that I can get? If I'm measuring energy, I'm measuring Hamiltonian. What are the possible values that I can get? I can get those eigenvalues, E1, E2, and E3. That's what we can get. H bar omega, 2H bar omega, 2H bar omega. Okay, so this is what we can get. Very good. But what is the probability to get them? Well, the probability to get the first one is given by this first element here, the absolute value square of this guy. Okay, so the probability to get this eigenvalue is that first one. So what is the probability? Is C1, that exponential absolute value square. What is the operation that we are doing here? Is the conjugate by itself. And so you see that the exponential plus with exponential minus becomes exponential of 0, is 1. So what we get here, C1 squared. Okay. What is the probability for this guy? Is the second one. Okay. The second one. And same story, we are going to get C2 squared. And finally, for the last one, the probability to get the last one is this. And what is that? Is C3 squared. But now forget, these two are the same number. Okay, so let's put all this together. We can say if we measure energy, we can get that energy h bar omega with probability C1 squared. We can also get energy 2h bar omega with probability. You cannot distinguish those two cases because they are equal. So with probability, C2 squared plus C3 squared. Okay, so that's the answer. All right, now let's go for one more. Remember what our evolved state is. Let me write it here again. We had C1 with this minus, C2 with this minus, and C3 with this. And now the question is, okay, but now instead of measuring energy, instead of measuring the Hamiltonian, suppose that you measure A, the observable A, that matrix A that we have, okay? What can we get when we measure A? And with what probability? Okay, so what are the eigenvalues of A? Now remember, if I'm measuring an observable, what are the outcomes that we can get? The eigenvalues. So for that A, we can get the outcome, the eigenvalue 2 lambda, or lambda, or minus lambda. And what is the probability of each one of them? Probability is how much of the vector that is given exists in the eigenvector of A1. In other words, what is the overlap between that evolved state and our vector A1? Okay, and absolute value square to get probability. That's how we get probability. Here, I didn't even tell you. I said, oh, it's just the first, just the second. Why? Because how did I get this first one? I did the same thing. How much of that evolved state exists in our eigenvector H1, absolute value square? But this eigenvector H1 is just 1, 0, 0. So that's why it was so simple. I just picked that first element directly. Okay, so then let's go down here to find the probability. Then when I measure the observable A, I will get this eigenvalue to lambda. How much, what is this probability? I have to do this inner product. Okay, so this inner product. We also say this overlap, absolute value square. This will give us the probability. Okay, all right, so then let's write this. This vector of 1 was a simple one, was that there was 0, 0, 1. The evolved state is what we have above. Okay, so I'm not going to write it again. It's this vector here. So you see that the only thing that will survive is this guy. No, see? And so the result here is going to be C3 squared. Okay, because this is a simple vector. But let's do the second one. The second one is more interesting. So when I measure the observable A, I can also get eigenvalue lambda. But with what probability? I have to do the overlap between my evolved state and the eigenvector alpha 2 and do the absolute value square. This is probability. So this vector here, this alpha 2 is the one that had 1 over square root of 2, 1, 1, 0. And we can rewrite our whole vector here again, C1 C2. I think here we have, here we have number 2, and then C3. Okay, so that's what we have to solve, and then do the absolute value square. So do here the absolute value square as well. All right, so let's do this, this inner product. What do we have? 1 with the first term, so we have C1 with that exponential, and then second term, C2 with that exponential. All this, at the end, I have to do the absolute value square. All right. Absolute value square means the square of that we can already put in front. Then we do complex conjugate. C conjugate plus I omega t. C conjugate plus 2I omega t. Multiply by itself. C1 with minus. C2 with minus. Okay. So that's the absolute value square. All right, so let's continue. 1/2, okay. This element with this, you see that the exponential will just give us 1. So this is fine, C1 square. Now the second one, this one with this, let's be careful here. We have C1 conjugate with C2. And then the exponential survives, minus I omega t. All right. These two, we have C2 conjugate with C1 and exponential plus I omega t. And then finally, the last one, this with this, the exponential does become 1. So we have just C2 square, right? So that's the probability. So this is the answer. This is the probability. So see, much more complicated now, no? This is the probability that if I measure the observable A, I will get the eigenvalue lambda. So this is the probability. Okay, and this probability, you see that this probability changes in time. No? It changes in time because of these terms. Okay, and that's the same thing. The same procedure you have to go on to obtain the probability to measure the other eigenvalue, and same story for the observable B. And I think this is good enough.